This will be mini lecture 14. And I'm going to do a little bit of a review, look back on what we did in lecture 13. We've introduced the Thevenin equivalent circuit model. And I made the comment that Thevenin and Norton models, the two models, are a major part of your exam number one. And again, if you want me to again reiterate what are the major parts, and I would say nodal analysis, mesh analysis, and now Thevenin and Norton models. They are the three big chunks, essentially, of exam number one. Again, we also need to be able to calculate power for resistors and sources. We also need to be able to do current voltage division and those sort of things. But the main chunks, the main components are those three pieces here. So we started discussion by looking at the Thevenin model. And so we made a case, I'm hoping successfully, why we need model. The kind of circuits we're looking at here are circuits that connect to the outside world via one pair of terminal. You can look at, for example, your car battery as such a circuit. You can look at a connected speaker, not a Bluetooth, obviously, although you could say that for Bluetooth because it's actually wireless. But you could look at a connected speaker that has one, a pair of wire coming down to connect from the receiver, as also the receiver being a one-port network. Anything that connects to the outside world via a pair of terminal can be looked upon as a one-port network. So this discussion here again, sometime it is important, useful to create a simple model, and I mean simple, but I don't mean inaccurate. The model is exact, and that's what's neat about the Thevenin model, and later on we're going to cover the Norton model today. The model is exact. It is important to come up with a model in case we need to vary the load, or we need to find what specific load would create a maximum power transfer to the load, that kind of thing. So there are questions we can answer a lot easier if we have a simple model. And the Thevenin model is at the bottom of the screen here, the bottom right. It is an ideal voltage source that we call VOC. The OC stands for open circuit, and you'll see why we call it VOC. There are some textbooks that call it VThevenin, so it's nothing wrong about that, but I like the VOC because it implies how to calculate it. And then in series with the source resistance, which we call the Thevenin resistance RTH. What I want you to know, what I want you to think right now as you see this, okay, I want you to think it is also a practical voltage source model. All right, so the Thevenin model is a practical voltage source model. So it actually makes perfect sense. And this thing is exact. So when I ask you for a Thevenin circuit, I am asking you to give me the model, what I'm showing you at the bottom right here. Again, the model has nothing to do with what it's being connected on. So the model has nothing to do with the load or network B here on my PowerPoint slide. The model is exclusively about the circuit you want to model. So when I ask you for a Thevenin equivalent circuit or Thevenin model or Thevenin equivalent model, whichever of those things is the same thing, you're looking at giving me the schematic of the circuit, which is what I have here on my bracket here at the bottom right of my screen. And then the next two steps is to calculate VOC, that's step one, and then calculate the Thevenin resistance, that's step two. So it's kind of a three-step answer when I ask you for a Thevenin model. Okay, so and then let me just briefly remind you, how do we get VOC? VOC is simply the reason why I like VOC. It's basically the voltage across A and B with nothing connected to it. It's the voltage across the circuit that you want to create the model for. It's as if we were to pick a voltmeter and measure the voltage across that circuit. Okay, so that's VOC, right? So it's the original circuit we want to model, just calculate the voltage across. So it's like taking your speaker offline and measuring the voltage that comes across the speaker wires, or looking at the voltage that come across your car battery. Okay, so, and we do this, generally speaking, mesh or nodal. Obviously, in the early part of the course, I might tell you do it using mesh, do it using nodal, but generally speaking, in the future, you are going to have to make some judgment what is the best method for you to solve that particular circuit. But we're generally speaking looking at mesh or nodal here. So that's VOC. How do we find RTH, or Thevenin resistance? The Thevenin resistance, you're going to see my kind of nomenclature when I do the crosshair thing. That means turning off all independent sources. You know it's independent sources because I have a circle as my symbol, as opposed to a diamond that is the dependent source. We never turn off dependent sources. No situation we do. So this means turning off all independent voltage sources and turning off all independent current sources. You need to know what happened when you turn what happened when you turn off an independent voltage source. It becomes a short circuit. And if you turn off an independent current source, we replace it by an open circuit because we want no current. Okay. So we've been looking at the simplest case that we can simply combine resistors. Later on, we're going to move on to a little bit more challenging case in the future. So that's essentially what we've been doing, finding the Thevenin model. So I'm going to go, let me pause here a little bit and show you the Norton model. So I'm going to show you the Norton model. So the Norton model essentially is at the bottom right of my screen. So the Thevenin model, I put on purpose, I put the Thevenin model above and the Norton model below. The Norton model, in essence, is a source transformation. Okay, so you can actually go from the Thevenin to the Norton model by simply do a source transformation. You'll notice that the Thevenin resistance is the same in both models, except for Norton, it's in parallel with the current source. And then the so-called ISC, which stands for I short circuit, again, you'll see why we say that. It's related to VOC by source transformation, given ISC is VOC divided by the Thevenin resistance. There's only one case this thing fails, actually, is when the Thevenin resistance is 0. Okay, it fails. Otherwise, it always works. So what I'm saying here, essentially, one way to get the Norton is to get the Thevenin circuit, and then you can use source transformation to get the Norton. You ought to be able to get the Norton circuit without going to the Thevenin, and I'm going to describe how that works. So the Norton model is a practical current source model. The independent current source value is ISC in parallel with the Thevenin resistance, the same Thevenin resistance we had for the same Thevenin we had for the Thevenin model. Okay, so we basically know how to calculate the Thevenin resistance. We're going to focus a little bit more how to calculate ISC, and then we'll do an example, and then I'm going to have you do one. Okay, so again, it fails for the case, the source transformation fails when the Thevenin resistance is 0. Otherwise, it works fine. So just to reaffirm, we're looking at the model, the Norton model is given at the bottom right. It's the practical current source model with an independent current source whose value is ISC. The SC stands for short circuit in parallel with the Thevenin resistance. How do we find ISC? Well, first, let me look at, again, I use the same slide that we found, what we use for the Thevenin model to find the Thevenin resistance. We turn off all independent sources, and we find the equivalent resistance looking in terminals A and B. Okay. ISC, which is why we call it ISC, stands for short circuit current. We physically short circuit A and B. Okay. We put a wire. And I have to tell you that many times students essentially struggle with that. Students tell me, well, yeah, I know it's short circuit, but they don't put a wire. You have to physically connect A to B and find the current that flows from A to B. What does that do from a circuit analysis model? If you think about node analysis, if I put a wire from A to B, then node A becomes node B. It's one node. If you don't put the wire physically, you're going to have two separate nodes. You can see how this thing doesn't work. In mesh, if I physically put a wire from A to B, I have another mesh current. So you need to physically put the wire and then calculate the current that flows from A to B. Okay, we're going to do a couple examples and have you do one. Okay, so we usually start small, and what I'm asking you essentially is find the Norton equivalent circuit. Sometimes I will say Norton equivalent model or Norton model for the network to the left of terminal A and B. What do I mean by that? I mean that the 4 ohm is not part of the model. Okay, that's what I mean by that. Without the 4 ohms. So everything except the 4 ohms, I'm looking at A and B. Without the 4 ohm is the load. Okay, and so it's a simple circuit. We want to find the Norton model for that. So again, you got to remember the Norton model is the bottom right. So I need ISC and the Thevenin resistance. So let's look at how do we find ISC. We physically short circuit, and that's what I was talking about here. We physically short circuit A and B. And when we do that, node A becomes node B. So in this particular example that I'm doing here, of course, I'm picking node analysis. That's pretty clear because I'm selecting a reference node, labeling the other nodes. The reference node is at the bottom, and then I label V1 and V2. And I'm going to, we're going to do a super node here. Obviously, I'm not going to do much with it. So sometimes I don't draw it because it has the reference node. And then I'm going to write one source equation for my voltage source, which will be V1 is equal to 6 volt. Okay. So V1 is equal to 6 volt. There's my reference. There's my super node that I won't do much about. So the source equation is right here. V1 is equal to 6 volt. And I have to do 1 KCL at node V2. Okay. So notice that ISC is the current under 3 ohms. So I'm not putting another current under 3 ohms. Don't add current when you don't need to. The current ISC is already the current on that 3 ohm. Okay. So I do my KCL at node V2. Current coming in equal current coming out. I1 is equal to I2 plus ISC. And then we go into Ohm's law, passive sign convention. I1 is V1 minus V2 divided by 2. I2 is V2 divided by 1. And then ISC is V2 divided by 3. So we take this 3, we put them in our KCL equations. We collect terms. Okay. And we have the second equations. We know V1 for this particular case. V1 is 6 volts, so I can easily solve for V2. So V2 is 18 over 11 volt. And from V2, I can calculate ISC, which is essentially V2 divided by the 3 ohm resistor. So ISC is 6 over 11. Okay. So that's our short circuit current for the Norton model. To find the Thevenin resistance, I again look into terminals A and B, turning off all independent sources. We now know what happened when we turn off a voltage source. We're going to replace this voltage source by a wire. So it's going to be this. Okay. So we replace the voltage source by a wire. So what do we have? These two things, these two resistors are clearly in parallel. And the net result is going to be in series with the 3 ohms. So we get 3.66 ohm. Simple problem, but it shows you the process for a Norton equivalent circuit or Norton model. Okay. So the model is the original circuit is on the right and the model is on the left. Not a whole. I mean, obviously the original circuit wasn't a complicated circuit, but on the other hand, for some complicated circuit, having that simple model would be very helpful. So that's the Norton equivalent circuit. So of course, we start with a simple example. I'm going to do a little bit more complicated example, and then I'm going to have you do one. So the second example to me illustrate why we need model. Okay, so again, obviously we're going to do it. We could answer this particular question with the Thevenin model as well, by the way. It doesn't have to be no Norton, but since we're looking for a Norton example, so we're going to use the Norton model for this. It's asking you to find the current IR, which is the current on the resistor R, going down the resistor R, for the values R being 2.5 ohms, 2.75 ohms, and 3 ohms. So 3 values. So if you didn't have the ability to create a model, we would need to solve this circuit using mesh or nodal 3 times. That's what we would do before. Now that we've essentially accumulated some sophistication in electric circuits, we're going to develop a model. We're going to develop the Norton model about, we're going to put A up here, B here, okay? We're going to develop a model for everything except the resistor R. And then when we get the model, we're going to connect the resistor R and be able to answer the question of the current for these three values by solving that basic circuit 3 times very simply, okay? So the first essentially part here, and you know, we're going to do it using current division. So the first part here is, again, I'm looking for the Norton model. So I short circuit A and B. Remember what I had here. So I had A, you know, let me put my A here. It might be here, okay? So R is not a part of the model, all right? So I can write better. R is not a part of the model, so I remove R, and then I short circuit A and B. I put a wire between A and B, basically. I short circuit A and B, and I'm finding the current ISC that flows from A to B. Oops, sorry, from A to B. Oops. Nope. I apologize. The slide jumped because I pressed a number and it jumps to a different number. So again, in this particular example here, we are seeking to find a Norton model. Let me just go back here. We're seeking to find a Norton model so that we can answer the current on the resistor R for 3 values of the resistor. So we create the simple model, and then we can connect the resistor R and then answer that question very simply. We're going to use current division after we do that. Okay, so the next step is to find the Norton model. I'm going to do a nodal analysis procedure here. I put my reference node at the bottom. This is actually an excellent reference node because that's going to give me the value. V4 and V3 are going to be known and easy equations to write. You're going to see that. I put current on all my resistors. The ISC is the current under 1 ohm, so I don't add another current to that. Okay, and then I label all my nodes, V1, V2, V3, and V4. Okay, so this is basically, I prepared a circuit for nodal solution. And then this is a case where we have 2 supernodes that share a common node, that bottom node, which is the reference node. So I combine them into a larger supernode. And then we write one source equation for each voltage source. In this particular case, for the 6-volt source, where the plus is, which is V4 minus 0 equals 6. And then for the 20 volt, where the plus is, which is V3 minus 0 equal 20 volt. These are easy equations to write. When you have voltage sources in nodal analysis, they're actually the easiest equation to write, if obviously if you're prepared and you don't have a phobia about how to treat voltage sources. Okay, so this is the case where the supernode here, that big supernode, has a reference node. So we don't do anything about, we don't do anything, no KCL about the supernode when it has a reference node. So I've got 2 equations here. My other 2 equations going to be a KCL at here at node V1 and a KCL at node V2. And here they are. KCL at node V1, excuse me, 10 coming in equal I2 plus I5. And if I look at node V2, I have I5 coming in, I7 coming in, I3 coming in, and then ISC leaving. So those are my 2 KCL equations, one at node V1, one at node V2. These are nodes that we call regular nodes. That means they're not the reference node and they're not connected to a voltage source. We're just going to go to Ohm's law and then substitute and solve for V1 and V2. So there, Ohm's law, I5. Again, these Ohm's law, I won't go through them. They're pretty normal, simple, passive sign convention. We bring the Ohm's law into the 2 KCL equations, and we solve for V1 and V2. We really need V2, because from V2, I get ISC. Okay, so V2, in fact, is equal to ISC, because ISC is V2 divided by 1 by virtue of Ohm's law. So ISC is 6M. So that's, you can see how this entire process relies heavily on knowing mesh, in this case, nodal analysis. Okay, so your comfort, your proficiency in mesh and nodal is going to be really important going forward in that class. All right, so that's ISC. How do we find the Thevenin resistance? I'm purposely keeping the source here, and I'm putting my crosshair to remind you what we're doing here. We turn off all independent sources. Standard question I'm going to ask you: what happened to a current source when it's turned off? what happened to a voltage source when it's turned off. The current source behaves like an open circuit, broken wires. And the voltage source turned off, we replace it by a wire, a short circuit. Okay, so the circuit we're really solving shouldn't have these sources when we're solving for the Thevenin resistance. So that's where the current, you can see where the current source was, and then the voltage source, our short circuit here. So, so in essence here, what do we have here? The 5 ohm is in series now with the 2, because whatever current is on the 5 ohm is also the current on the 2 ohms, right? Because there is nothing on the left, it's just broken wires here. So the 5 and the 2 are in series. That combination, which is 7, is going to be in parallel with the 7. So that's going to give me 3.5. These two things are going to be in parallel. Okay. All right. And then that 3.5 is going to be in parallel with the 1 ohm. In parallel, actually, with the 3.5 ohm on the other side. Okay. And in series with the 1 ohm. All right. So that's what you got. So the 3.5, that combination here, it's going to be. So let me do this on paper here. Let's do this, because that's a little bit of an interesting circuit. Let me just do this on paper. Just give me a second until I warm up my document camera here. All right. So let me just draw the circuit here. What we have. Okay, so let me just go to the document camera and hopefully it will cooperate nicely. All right, so this is the circuit and we're looking for the Thevenin resistance, looking into A and B. All right, so again, if you feel comfortable when you're combining resistance, do it step by step. Do it step by step. It's better to show your work and show your work step by step, as opposed to doing something that doesn't work. So what I'm going to do here, I can clearly see that these two are in series, right? Because this is an open circuit. The current on the 2 ohm and the current on the 5 ohm are the same. So what do we get here? The first step here, I'm going to have 7 ohm. The 7 ohm essentially is 5 plus 2. So it's going to be in parallel with another 7 ohm. There is A and B, and there is my 1 ohm. And then there's my 3.5 ohm. Okay? So that's what we get here. So that's the first step, is just combining the 5 and the 2 in series, 5 plus 2. Okay, that's how we get the 7 ohms right there. You can now see these two are in parallel. So I'm going to combine them. And when we combine two resistors in parallel of the same value, you get half the value. So what do we get here? We get 3.5 ohm. A, B, there's the 1 ohm. Oops, 3.5. So that's what we got here. Okay, that's a new circuit here. All right. So, and you can kind of see that these 3.5, they are actually in parallel. So we combine them in parallel. Then what do we have? We have 1, which is 1.25 ohm. A and B. And we get there. And now you can clearly see these two are in series. So RTH equal to 2.25. Okay. So if you have any compunction about, combining resistors, just take a little bit of paper and do this. Do it step by step. It's going to avoid you a lot of points lost for sometimes really basic circuit solutions. Okay. Just wanted to show you that as a good example of good practice for you when you're solving circuits. Okay, let's go back. So again, 2.75. I'm getting 2.75. Let's see here. Yeah, that may be a mistake, but let's take the 2.75 as it is. So now I connect, this is my Norton model here. This is a Norton model. And then now I'm connecting the resistor R. And then I'm essentially saying, okay, for R equal 2.5, I can use current division and get that current IR using current division. So that's 3.14. And again, then I can redo this for R equal 2.75. This is a simple circuit to solve. And then, of course, for R equal 3 ohm, I can do the same thing. So you get the sense of why models are important using these examples. All right. I'm actually going to put a new example for you, and I'm going to ask you to take some time and develop the Norton model. So this is the example that I'd like you to take some time doing. So this is asking you to use the Norton equivalent model, Norton equivalent circuit, to calculate the current I on the 50 ohm. What does that mean? That means we're going to put our node A here and our node B here. Okay. We're going to put our node A here and our node B at the bottom. And the model does not include the 50 ohm. The model essentially is without the 50 ohm. And after we get the model, we're going to essentially connect the 50 ohm and calculate the current through it. I know it's not really saving us work, but it shows us the process and, in terms of finding the model, and then you're using the model to answer a different question. So I want you to pause this video or, essentially stop it right there and come back to it. So give yourself about half hour for this, okay? Again, when we talk about the Norton model, we are talking about, what the model schematic is. That is a practical current source model. The independent current source is ISC. The resistance is the Thevenin resistance in parallel with the independent current source. And then you proceed to calculate ISC and the Thevenin resistance, and then you come back and answer that question. So please pause the video and then restart it whenever you want at that point so that you can look at the solution. It's crucial that you actually do that work instead of watching me do it. So assuming you've done the work, so what is the step? Again, that I put it on a slide so that you get it pretty much. I want you to start thinking that the model is a model to be used to answer a different question. All right, that's so what do we do here? We find the Norton model for the circuit on the right. You realize that I don't have the 50 ohm resistor in there. All right, my terminals are A and B. That's what connects to the outside. Well, then I'm going to connect the 50 ohm and find its current after that. So the first part of that is to find the model. All right. So, and in the model, again, the model. I'll put the model at the end. The first thing is to find ISC. I'm calling it IS right now just because I needed space, but it's ISC, which is short circuit A and B in finding the current flowing from A to B. So this is a particular problem where you might be thinking, okay, what method do I use? Do I use mesh? Do I use nodal? If I did mesh, I would have 1, 2, 3, 4 meshes, and obviously nodal. Let's see, one node. I think only 3 nodes here. So I'm going to do nodal. How's that? Okay. 4 nodes with the only 3 unknowns, 4 nodes with the reference node. Now, this is the challenge that many students are not going to see here, is that once you essentially short circuit A and B, this entire thing becomes 1 node. This entire thing is 1 node. Okay. So you need to be mindful of that when you short circuit, again, terminal A and B, that node A becomes node B, and that makes this entire thing 1 node. If I did it, on the other hand, if I did mesh, I'm going to do nodal here, I would have an extra mesh current here. Okay. So mesh adds an extra mesh when you're doing the ISC calculation in Norton, and then node will essentially eliminate one node. So that's just basically something in ballpark that I want you to think about here. Okay. All right. So I'm going to do nodal analysis here. So I'm purposely exaggerating that node to show you that. And I create super node around my voltage sources. And in this case, there's two super nodes share a common node, the reference node. So I combine them into one big super node. And then I write my two source equation, one for each voltage source. Okay. In the case we have for the 10 volt, I have V3 minus 0 equal 10 volt. And for the 5 volt, I have 0 minus V2 equal 5 volt. These are easy equations to write, okay, particularly when you have independent sources. There's, usually you write the equation and have no work to do after that. And then what's left? I'm not going to do KCL about the super node because it has a reference node. I'm only doing one KCL at node V1. A regular node V1. So let me put some currents on my resistors. So I put some current on my resistors, and then I do KCL at node V1, which is I1 equal I2 plus I3. Okay. All right. And then you can see me moving the 10 volt to the node and the minus 5 volt to the node. Be careful at doing that. I actually prefer you to leave it as an equation instead of doing what I'm doing, because that ends up making your calculation a little bit more challenging for some students. So if you actually, instead of doing I1 is 10 minus V1, again, it would have been a little bit better to say I1 is V3, this is V3 here, V3 minus V1 divided by 30, and leave the 10 volt as an equation so that you don't get into all these algebraic error possibilities. Okay. So we put these things in, and then we calculate V1. V1 is minus 0.909 volt. Okay. So we have all of the node voltages. A challenge here is to calculate IS. Which is my ISC. I need this current here. So we're done with nodal analysis here. Totally done. But I can do a KCL right here. Not part of nodal. That would be illegal because that would be my reference node. But I can do it here because I want the current IS that's coming down that wire. So basically, if I do that, okay, you can see that IS is going to be I3 plus I2 minus 5. The 40 ohm gets no current because it's short circuit. The 40 ohm essentially, the current on the 40 ohm is 0 because it's that node minus the reference node. It's the reference node minus the reference node divided by 40. It's 0. So that's a little trickier. I grant you that. So IS is 5 amp plus I3 plus I2. And using Ohm's law for I2 and I3, I get the current IS, which is ISC, called 5.36 amp. A little challenging, okay, in terms of that. Actually, it would be a good exercise for you to redo this problem here using mesh. It will be a good practice for that. Okay, so next thing I'm going to do, I am going to turn off all independent sources. So that's what you see me. They're getting dotted here. So I'm just going to turn these things off. And standard question, what happens when you turn off a current source? What happens when you turn off a voltage source? The voltage source becomes a wire. The current source becomes open circuit, broken wires. So you're really solving this. Okay, you're really solving this. Again, I encourage you to do it on paper, step by step. I can see that these two are in parallel. Okay, and the net result is going to be in series with the 30, and that net results would be in parallel with the 40. My Thevenin resistance, 19.13. Do it on paper step by step. Okay. So this is then what we do. We now connect the 50 ohm, and we can calculate by current division. We can calculate the current on it, which is 1.48 amps. Okay. We're going to do some more challenging problem in the future lectures. We're going to probably have at least a couple mini lecture on Thevenin and Norton model, increasingly doing some challenging problems. The next one, we're going to learn how to treat circuits that we cannot just simply combine resistance. Okay. Thank you very much.